Good evening and welcome into the Science Files. I'm Madeline Rowe, and tonight we're opening a record built from signals so brief that most of them crossed a telescope's field of view, entered a receiver, and ended before any human being knew they had arrived. They are called fast radio bursts. Intense flashes of radio emission that last for milliseconds often come from galaxies far beyond the Milky Way and still resist a single, complete explanation. We'll follow the evidence preserved in their frequency sweeps, their arrival times, their polarization, their host galaxies, and the rare occasions when a source has repeated long enough to be located. We'll examine the event that connected at least one of these bursts to a magnetar in our own galaxy, and the later discoveries that prevented that answer from becoming too simple. And if you enjoy these calm, evidence-backed case files, please subscribe. There will be another one waiting for you soon. Back in my office, where the outer hull narrows beneath the forward observation dome, shelves, old data ports, and panels of dark glass enclose the shallow room. Most evenings, the dome is dark enough to behave like a mirror. I can see the desk lamp, the edge of the cartography cabinet, and the pale status lights running along the ceiling. Beyond those reflections are stars, although the glass gives no sign that they are moving. The ship crosses enormous distances without changing the appearance of the sky very much. On the desk tonight is no photograph of a planet, no mineral sample, no diagram of an animal or a machine. There is only a strip of data. It is long and narrow, marked with time along one edge and radio frequency along the other. A sloping streak crosses it from upper left to lower right. The trace is faint at first, stronger near the centre, then gone. If I correct the arrival times, delaying one part of the record and advancing another, the diagonal streak collapses into a single, narrow pulse. For a few milliseconds, a distant source became one of the brightest radio emitters visible from Earth. Then it stopped. The old file gives this class of event a name: Fast Radio Burst, FRB. The name describes the evidence with care. Fast, because the emission is brief. Radio, because the energy was recorded at radio frequencies. Burst, because the signal appears suddenly rather than as a steady source. The term does not identify an engine. It does not imply a message. It says nothing about purpose. In astronomy, a signal is simply something measured by an instrument. The missing sender in this case is physical, the object, environment, and mechanism that produced the emission. The first widely recognised example had already been sitting in an archive for several years before anyone understood what it was. In 2001, the Parkes radio telescope in Australia was surveying the region around the Magellanic Clouds. Parkes was a large steerable dish with a multi-beam receiver, capable of recording several neighbouring regions of the sky at once. The survey had been designed largely for pulsar work. Its data contained time, frequency, and intensity measurements, preserved in the expectation that periodic radio sources might be found later. A graduate student named David Narkovich searched those records for individual pulses. In one observation made on the 24th of August 2001, the software found something extraordinary. The event was eventually analysed by Duncan Lorimer, Maura McLaughlin, Matthew Bales, Narkovich, and Fronefield Crawford. Their paper appeared in 2007. The burst lasted less than about 5 milliseconds at the available resolution. Its estimated peak flux density was around 30 Janskys, an immense value for such a brief event. It was detected in 3 adjacent beams of the Parkes receiver, which helped constrain its position and made an ordinary receiver fault less likely. More important was the shape of the signal in frequency and time. The high-frequency radio waves arrived first. Lower frequencies followed, delayed in a smooth and very particular way. Radio waves move through empty space at the speed of light. Interstellar and intergalactic space, however, are not perfectly empty. They contain free electrons. A radio pulse travelling through this thin plasma experiences a frequency-dependent delay. Lower frequency components travel slightly more slowly through the medium than higher frequency components. Over astronomical distances, the accumulated delay becomes measurable. The amount of delay depends on the integrated number of free electrons along the line of sight. Astronomers call that quantity the dispersion measure, usually shortened to dm. It is expressed in units that combine electron density and distance, most commonly parsecs per cubic centimetre. The unit looks unusual because dm is not a local density. It is the sum of electron density over the entire path between the source and the telescope. The Parkes burst had a dispersion measure of roughly 375 parsecs per cubic centimetre. Models of the Milky Way's free electron content predicted only a small fraction of that value in the direction of the burst. If the models were broadly correct, most of the dispersing material had to lie beyond the galaxy or within an unusually dense local environment around the source. The frequency delay also followed the relation expected for a cold ionized plasma. It was not merely a sweep that happened to move downward through the receiver band. Its timing matched known propagation physics. The burst showed signs of scattering as well. A perfectly sharp radio pulse can be broadened when different parts of the wavefront follow slightly different paths through irregular plasma. The result can be a tail that is stronger at lower frequencies. The observed broadening of the Parkes event was consistent with the sort of frequency dependence expected from turbulent ionized material. No second burst appeared during approximately 90 hours of follow-up observations. With only one event, the original investigators had to consider possibilities that later evidence would narrow or reject. A singular explosion was possible. A neutron star merger, a supernova-related event, or another catastrophic source might have produced one flash and never repeated. The inferred distance was uncertain, although the excess dispersion suggested an extragalactic origin. The event became known as the Lorimer Burst. At the time, it was difficult to know whether a new astronomical population had been found, or whether an unusual terrestrial signal had passed through the analysis. Radio telescopes live inside an environment crowded with human transmissions. Radar, satellites, aircraft, electronics, mobile communications, and electrical machinery can all produce interference. A false signal may enter through a side lobe of the telescope rather than through the main beam. Some interference changes in frequency with time. Some of it appears only once. The Parkes telescope later detected events called peritons, named after a mythological creature whose shadow was said to resemble a human shape. Peritons looked dispersed at first glance, but they differed from astronomical bursts in revealing ways. They often appeared across all 13 beams of the receiver, suggesting a nearby source rather than a point in the distant sky. They clustered at certain times of day. Eventually, investigators traced them to microwave ovens at the observatory. Opening an oven door before the timer completed could interrupt the magnetron, in a way that released a brief burst of radio frequency interference. This did not explain the Lorimer Burst. It showed why the standards of proof had to remain high. A genuine celestial pulse should behave consistently with propagation through plasma. It should appear in a telescope beam pattern compatible with a source on the sky. It should not follow the habits of machinery on the ground. Independent telescopes should eventually detect similar events from unrelated directions. For several years, the evidence remained sparse. Then additional bursts were reported. In 2013, a team led by Dan Thornton published 4 new events found in a high-latitude survey at Parkes. Their dispersion measures were again well above the expected contributions from the Milky Way. The bursts came from widely separated directions. Their inferred occurrence rate suggested that the sky might produce thousands of detectable events each day above a given sensitivity threshold, even though any one telescope observes only a small fraction of the sky at a time. The case changed. The Lorimer Burst was no longer a solitary anomaly. It belonged to a population. I leave the office and carry the restored record into the instrument room. The door closes behind me with a precious seal that I feel more than hear. Long receiver racks line both walls. Most are dormant. A few still process navigation signals, map charged particles around the ship, or listen for changes in the local plasma. Their displays divide incoming radiation into narrow channels. That division is how a dispersed radio pulse becomes visible. A radio receiver does not hear an FRB as a human ear hears a sound. The instrument measures electromagnetic energy across a range of frequencies. The incoming signal is sampled rapidly, often in intervals of milliseconds or less, and recorded as a dynamic spectrum. Time runs along one axis, frequency runs along the other. Brightness is represented by intensity. If a broadband pulse arrived through a perfect vacuum, its energy would reach all frequency channels at nearly the same time, aside from effects introduced at the source or by the instrument. Through plasma, the pulse bends into a sweep. At lower radio frequencies, the delay can span seconds relative to the higher frequencies, even though the burst itself may be intrinsically far shorter. Search pipelines test many possible dispersion measures. For each trial, DM, the software shifts the frequency channels by the delay predicted for that electron column. When the correct value is used, the dispersed signal aligns. Energy that had been spread across time adds together into a narrow, detectable peak. This process is called de-dispersion. It is one reason FRBs could be recovered from surveys that were not originally designed to find them. The raw data preserved the frequency structure. Later software could search through many possible DMs and pulse widths, looking for a signal that became sharper when the correct propagation delay was removed. Dispersion provides evidence, but it must be interpreted carefully. The measured DM is the total contribution of every ionized region crossed by the pulse. There is plasma in the Milky Way's disk and halo. There is plasma between galaxies. The host galaxy contributes its own electrons. Gas close to the source may add a large and variable component. A large DM therefore does not function as an exact distance measurement. Two sources at the same redshift can have different DMs because their sightlines pass through different structures. A source embedded in a dense nebula may appear more dispersed than a more distant source in a cleaner environment. Models of the Milky Way's electron distribution introduce their own uncertainty. Even so, the early FRBs had DMs too large to fit comfortably inside the galaxy. Their distribution across the sky was broadly consistent with an extragalactic population. Later localizations would confirm that inference directly. Before astronomers could locate the sources, the bursts themselves already imposed severe physical constraints. A millisecond is 1,000th of a second. Light travels about 300 kilometers in that time. A source that changes over a millisecond cannot usually be larger than the distance over which information could cross it during the change, unless relativistic motion, geometry, or propagation modifies the observed timescale. That does not mean every FRB is emitted by an object exactly a few hundred kilometers wide. The duration may be shaped by a narrow beam sweeping past the observer, by emission from a relativistic outflow, by several unresolved subpulses, or by scattering. It does, however, point toward compact systems. Neutron stars immediately became serious candidates. Distance made the problem sharper. A source in another galaxy must release much more power than a nearby transmitter to produce the same measured flux at Earth. Once FRBs were associated with cosmological distances, their inferred luminosities became extreme. Astronomers often describe this through brightness temperature. The term does not mean the emitting matter is literally heated to that temperature. It is a way of expressing how intense the radiation would be if it came from an ordinary incoherent thermal source of a given angular size. For FRBs, the implied brightness temperatures can reach values around 10 to the 35th Kelvin or higher, depending on the event and assumptions. No material could remain in thermal equilibrium at such a temperature. The number tells us that ordinary incoherent emission is inadequate. In most hot sources, charged particles radiate independently. Their waves add with random phases. Coherent radio emission is different. Many charges radiate in a coordinated manner, allowing their electric fields to reinforce one another. Pulsars do this. Some solar and planetary radio emissions do it. Laboratory masers do it under controlled conditions. FRBs require coherence on a scale and at an intensity that remain difficult to derive from first principles. The central problem can be divided into several layers. There is the engine, the object or system supplying the energy. There is the region where the radio emission forms. And there is the plasma process that converts energy into a coherent millisecond pulse. A magnetar may provide the engine while leaving the emission mechanism uncertain. The radio waves might be produced inside the magnetosphere, where fields and particles are tied closely to the neutron star. They might form farther away when an outflow drives a relativistic shock into surrounding material. Different bursts may not use the same route. During the early years, theoretical papers proposed a long list of engines. Some involved compact object mergers, collapsing neutron stars, evaporating black holes, interacting white dwarfs, flaring stars, active galactic nuclei, superconducting cosmic strings, or artificial transmitters. Many were responses to a small and incomplete data set. As observations accumulated, models were removed or narrowed. Any proposed source had to satisfy the burst duration, energy, event rate, polarization, spectrum, repetition behavior, host environment, and lack or presence of radiation at other wavelengths. It also had to allow the radio pulse to escape through the surrounding plasma without being absorbed or scattered beyond recognition. The most useful evidence did not come from adding more ideas. It came from finding bursts that behaved differently from what the first detections had suggested. The first decisive change arrived from a source known at the time as FRB 121102. Its original burst had been detected with the Arecibo telescope in Puerto Rico. Like other FRBs, it had a dispersion measure above the expected galactic contribution. Initial follow-up found nothing. Then more extensive observations were conducted. In 2016, Laura Spittler and her colleagues reported 10 additional bursts from the same direction. Their positions were consistent within the Arecibo beam. Their dispersion measures matched. The frequency delay law was consistent with propagation through a cold ionized plasma. The source had repeated. That one fact eliminated a large family of explanations as universal models. A neutron star merger destroys or radically transforms the original system. A terminal collapse does not reset and happen again. A source producing repeated bursts must survive the release of energy. This did not prove that every FRB repeated. It showed that at least one did. The bursts from FRB 121102 varied in strength and spectral shape. Some were brighter at higher frequencies, others favoured lower frequencies. Several had multiple peaks. The activity was clustered, with many bursts in some observing sessions and none in others. There was no simple clock. The source behaved less like a bomb and more like an engine with irregular episodes of activity. I reached the holographic evidence bay through the corridor outside the research section. The room was once used to compare survey maps gathered by different instruments. Its projectors are old, but they can still turn a position estimate into a volume of light. I load the Arecibo localization first. It appears as a broad region suspended above the floor. Many stars and faint galaxies lie inside it. A source could be anywhere within the volume. The telescope had recorded the burst, but a single dish could not determine its position precisely enough to identify a host. Repetition offered a solution. Astronomers could point an interferometer towards the source and wait. An interferometer combines signals from multiple antennas separated across a landscape. The slight differences in arrival time and phase at each antenna encode position. With careful calibration, the array can localize a radio source far more precisely than a single dish of comparable size. The Carl G. Jansky Very Large Array in New Mexico was used to observe FRB 121102. Over many hours, it detected 9 bursts in a frequency band around 3 GHz. Because the array recorded the bursts with spatial information, each event could be imaged directly. The broad uncertainty region collapsed to a position accurate to roughly 1/10 of an arcsecond, about 3 orders of magnitude better than the earlier Arecibo location. At the same position, the VLA found a persistent radio source. It was faint, compact, and non-thermal. Optical images showed an equally faint counterpart. Very long baseline interferometry constrained the radio source to an even smaller angular scale. The signal now had an address. Optical observations with the Gemini North Telescope separated the light of the counterpart into a spectrum. Emission lines identified the host as a low metallicity, star-forming dwarf galaxy at a redshift of about 0.193. In the cosmology used by the investigators, its luminosity distance was close to 1 billion parsecs. This was direct confirmation that at least one repeating FRB source lay at a cosmological distance. The host galaxy mattered for more than distance. A small star-forming galaxy could contain young massive stars, supernova remnants, and recently formed neutron stars. Similar galaxies host some long gamma-ray bursts and superluminous supernovae. A young magnetar created in an energetic stellar explosion became an attractive explanation. The persistent radio source might have been a nebula powered by a young neutron star. It might have been associated with a low luminosity active galactic nucleus. Early data did not force a single answer. FRB121102 was the first source studied in such detail, and that made it tempting to treat its environment as typical. Later observations showed that this was unsafe. FRBs occupy a range of host galaxies and local environments. The first clear address was one example, not a template for the full population. Still, the localization changed the field. It demonstrated a method. Detect the burst, save high time resolution voltage data, reconstruct the position interferometrically, identify a host, measure its redshift, then compare the local environment with possible progenitors. Each successful localization converted part of the dispersion measure from a vague distance clue into a quantity that could be compared with a known distance. The case was becoming less anonymous, yet locating a source did not explain how it made the burst. The high-resolution radio records of FRB121102 revealed structures finer than the original category name suggested. A burst that looked like one pulse at low resolution could split into several components. Some subbursts occupied only part of the observing band. Their central frequencies drifted downward with time after the ordinary cold plasma dispersion had already been removed. This pattern became informally known as the sad trombone effect. The name is lighter than the evidence. In dynamic spectra, the components often form descending tracks, with later emission appearing at lower frequencies. For FRB121102, some subbursts lasted only fractions of a millisecond and occupied bandwidths of a few hundred megahertz. At higher observing frequencies, both the bandwidth and drift rate could increase. The drift might be intrinsic to the emission process. A disturbance moving through a magnetosphere or outflow could produce progressively lower frequency radiation. The source geometry might cause different emitting regions to enter view in sequence. Plasma near the source might delay or lend some frequencies more than others. The observations alone do not yet select one explanation. Even the best dispersion measure becomes subtle when a burst contains intrinsic frequency-dependent structure. A DM chosen to maximize signal to noise may differ slightly from one chosen to make the fine subbursts appear sharpest. If some delay comes from source physics rather than propagation, forcing all structure into the cold plasma formula can blur the very features astronomers want to study. This is a recurring difficulty in the case. The signal is shaped by both the engine and the path. The telescope receives their combined result. In the maintenance passage near the ship's forward sensor spine, cables and coolant channels run behind removable metal panels. A test pulse sent through a damaged line may arrive weakened, broadened, or reflected. The line did not create the pulse, but it altered what the receiver measured. Interstellar plasma is far more diffuse than anything inside the hull, and electromagnetic propagation through it follows different physics from a guided signal in a cable. The distinction is still useful. Some features belong to the source, others are imposed in transit, several can arise from both. Scattering broadens pulses when radio waves take multiple paths through irregular plasma. Scintillation changes apparent brightness with frequency and time, much as starlight flickers after passing through Earth's turbulent atmosphere. Plasma lensing can focus or defocus radio emission. Faraday rotation changes the orientation of linear polarization as a wave moves through magnetized plasma. Polarization gives another layer of evidence. Radio emission can be linearly or circularly polarized, depending on how charges move and how the waves propagate. Some FRBs show a high degree of linear polarization. The polarization angle may remain nearly constant across a burst or swing with time. These patterns can constrain magnetic geometry near the source. Faraday rotation depends on both free electrons and the component of magnetic field along the line of sight. Astronomers quantify it with the rotation measure, or RM, FRB 121102, displayed an enormous rotation measure, among the largest observed for a radio source. It also changed over time. That placed the source in an extreme and evolving magneto-ionic environment. Possible settings included a young magnetar nebula, a supernova remnant, or a region near a massive black hole. The measurement did not identify the engine on its own, but it revealed conditions around it. Other repeaters showed different polarization behavior. Some had much lower rotation measures, some varied in sign, some displayed circular polarization. The diversity again warned against building the entire class from one source. Timing offered another clue. FRB bursts are often irregular. They cluster during active periods and vanish during long observations. Researchers searched for periodicity across many timescales. A neutron star rotates, so a direct connection between burst arrival and spin might be expected in some models. Binary motion or precession could modulate when a source is visible. In 2020, the CHIME collaboration reported that bursts from FRB 2018096b were confined to a repeating cycle of approximately 16.35 days. In the initial sample, all 38 bursts arrived within a phase window lasting about 5 days, and half were concentrated within a much narrower interval. This was periodic activity, not a burst every 16 days. Within the active window, the individual pulses remained sporadic. Several mechanisms could produce such a cycle. The source might orbit a companion, passing through regions of wind or absorption. A precessing neutron star or magnetosphere might bring a beam into view. The surrounding plasma might periodically amplify or block the radio waves. The evidence established modulation. It did not reveal the clockwork behind it. The source itself had been localized to a star-forming region in a nearby spiral galaxy, strengthening the connection to young stellar populations. Yet even here, the activity cycle admitted several physical interpretations. By this point, the file held a growing number of constraints. The sources were compact. They produced coherent emission, some repeated, some lived in star-forming regions. Their signals crossed dense, magnetized plasma. At least one showed a cycle of activity. Magnetars had moved close to the center of the investigation. A neutron star forms when the core of a massive star collapses. The remnant packs more mass than the Sun into a sphere roughly the size of a city. A magnetar is a neutron star with an exceptionally strong magnetic field, commonly inferred to reach around 10 to the 14 or 10 to the 15 Gauss at the surface. Those fields store vast energy. Magnetars produce X-ray bursts, gamma-ray flares, changes in spin, and episodes of radio emission. Their crusts and magnetic fields can rearrange under stress. Currents flow through their magnetospheres. Sudden magnetic activity can accelerate particles and launch outflows. For years, these properties made magnetars persuasive FRB candidates. They offered compactness, energy, magnetic fields, and recurrent activity. What was missing was a direct event. That changed on the 28th of April 2020. The Galactic Magnetar SGR 1935+2 154 had entered an active state, producing multiple X-ray bursts. It lay within the Milky Way at an estimated distance of several kiloparsecs. If a source so close produced an FRB, the radio signal should be extraordinarily bright compared with events in other galaxies. CHIME detected a powerful dispersed radio burst from the direction of the magnetar. The event contained two main radio components separated by about 29 milliseconds. The signal was so strong that it appeared in many of CHIME's formed beams, even though the source was far from the telescope's primary observing direction. At higher radio frequencies, an array called STARE-2 independently detected the event. STARE-2 had stations separated across the southwestern United States and was designed to monitor a large fraction of the sky for exceptionally bright millisecond radio bursts. Space-based high-energy instruments detected an X-ray burst from SGUR 1935+2 154 at essentially the same time. The radio direction, the dispersion measure, the timing, and the X-ray activity all pointed to the magnetar. This was not a statistical association with a type of host galaxy. It was a specific galactic object producing a burst with FRB-like properties. The radio event is often called FRB 200428 or ST 200428AA in the STARE-2 analysis. Its energy exceeded that of previously observed millisecond galactic radio bursts by orders of magnitude. CHIME measured two components in the 400 to 800 MHz band. STARE-2 measured a much larger fluence, around 1.4 GHz, revealing strong spectral structure across frequency. Depending on the adopted distance and bandwidth, the inferred radio energy lay below many cosmological FRBs, but approached the low-energy end of the extragalactic population. A magnetar had been caught producing an FRB-like radio flash. The result answered one part of the case. Magnetars were physically capable of generating such events. It did not close the file. Most high-energy bursts from SGR 1935+2 154 were not accompanied by radio bursts detectable as FRBs. The 2020 event was unusual even within the magnetar's active episode. Many cosmological FRBs are far more luminous. Their local environments differ. Their repetition rates span a wide range. Some show persistent radio sources, while others do not. The simultaneous X-ray burst linked the radio emission to magnetar activity, but it did not reveal exactly where or how the radio waves formed. I bring the synchronized records into the central archive chamber. The room is circular with an old timing standard mounted behind glass at its center. Around it, separate data streams can be aligned to a common clock. CHIME's lower frequency radio trace occupies one section of the display. STARE 2's higher frequency detection appears beside it. The X-ray record lies above them. Once the light travel corrections and timing systems are reconciled, the events line up. Independent instruments had witnessed different parts of the same physical disturbance. This is among the strongest forms of astronomical evidence. No telescope saw the Magnetar's magnetosphere in detail. No probe sampled its plasma. The source was identified by consistency across direction, timing, dispersion, and high-energy activity. The remaining physics branches into two broad families of models. In magnetospheric models, the radio emission is generated close to the neutron star. A sudden magnetic disturbance may reorganize electric currents, accelerate charge bunches, or trigger coherent radiation along curved magnetic field lines. Pulsar-like processes are often invoked, although FRB intensities push them into an extreme regime. Coherent curvature radiation is one possibility. Charged particles moving along curved magnetic fields radiate. If many particles radiate with correlated phases, the signal can become coherent. The difficulty is explaining how the charge bunches form, remain organized, produce the observed spectra, and allow the radiation to escape. Other magnetospheric proposals involve maser processes, coherent inverse Compton emission, or reconnection-driven structures. Each must contend with the dense plasma and intense field near the star. A radio wave can be absorbed, scattered, or altered before leaving the magnetosphere. In external shock models, a magnetar flare launches a relativistic shell or pulse into surrounding material. When the outflow collides with earlier ejecta or a magnetized wind, a shock forms. A synchrotron maser or related plasma instability may convert some of the shock energy into coherent radio emission. These models naturally connect the burst to a violent outflow and can produce radio waves farther from the star, where escape may be easier. They must still reproduce millisecond structure, high efficiency, polarization, repetition, and the diversity of burst spectra. They may predict afterglows or high-energy counterparts that are not always observed. The two families are not equally favoured for every source, and neither has been demonstrated as the universal mechanism. The engine question and the emission question remain separate. A magnetar can power both magnetospheric and shock-based scenarios. Identifying the engine does not tell us where the radio pulse was assembled. Some recent measurements have constrained emitting regions for individual bursts to scales compatible with neutron star magnetospheres, using scintillation and polarization geometry. Those results strengthen close-in emission models for those cases. They do not automatically transfer to every FRB. A population can share an engine while using more than one emission channel. It can also contain more than one engine. The next major clues came from environments where young magnetars were not expected to be common. A repeating source designated FRB 200100120E was discovered in the direction of M81, a nearby spiral galaxy about 3.6 megaparsecs away. Its low dispersion measure and proximity made it unusually accessible. Very long baseline interferometry localized its bursts with milliarcs-second precision. The position fell inside a globular cluster associated with M81. Globular clusters are ancient, dense collections of stars. Their massive, short-lived stars disappeared long ago. ordinary core collapse supernovae, the standard route to young neutron stars and magnetars, should now be rare. The localization challenged the idea that every repeating FRB came from a newly born magnetar inside a recent supernova remnant. It did not exclude a magnetar. Dense stellar systems create compact binaries through close encounters. White dwarfs can merge. A white dwarf may gain mass from a companion and collapse into a neutron star. Neutron stars can merge or undergo interactions that alter their magnetic fields. These delayed pathways can produce a highly magnetized neutron star long after the original generation of massive stars is gone. The M81 source therefore changed the formation question. If its engine was a magnetar, that magnetar probably did not form through the same recent core collapse channel proposed for FRB 121102. The bursts themselves were also unusually brief and faint compared with many cosmological FRBs. Some contained structure on nanosecond scales. Its closeness allowed astronomers to detect lower energy emission that would have been invisible at greater distance. Selection effects matter here. Telescopes do not observe an unbiased sample of all FRB activity. They preferentially find bright bursts, active sources, favourable spectra, and events that occur while the right part of the sky is being monitored. A nearby weak repeater may reveal a population that exists elsewhere, but falls below detection thresholds. Another repeater, FRB 202402009A, complicated the environmental picture again. It was localized to the outskirts of a massive quiescent galaxy, at a projected distance of roughly 40 kiloparsecs from the galaxy's center. The host showed little current star formation. The burst location had the largest known offset of its kind at the time of the study. A globular cluster origin was considered plausible, perhaps the most likely interpretation. An undetected satellite galaxy or a compact object kicked far from its birthplace could not be completely ruled out. The evidence supported a delayed formation channel. It did not prove the exact local environment, and it did not establish a different engine. These discoveries created several viable possibilities. The FRB population might be powered mainly by neutron stars that form through several routes. Young magnetars could dominate star-forming regions, while older systems arise through white dwarf collapse or mergers. Some bursts might come from other neutron star configurations. A minority might be produced by catastrophic events and never repeat. The host galaxies alone cannot choose between those options. They set boundary conditions. I passed through the specimen archive, although no biological specimens are stored there now. The cabinets contain environmental records gathered during earlier surveys, stellar populations, gas spectra, magnetic field estimates, supernova remnants, star clusters. I place 4 reconstructed host scenes on the central table. One is a small star-forming dwarf galaxy. Another is a region in a spiral arm. A third is an old globular cluster. The fourth lies far from the luminous center of an elliptical galaxy. The same observational label, fast radio burst, appears beside each. Categories are useful because they gather similar evidence. They can also hide diversity. A physician on old Earth might have grouped many illnesses by fever before learning that different pathogens and processes could raise body temperature. Astronomers may be using one name for bursts created by a family of related engines, or by several distinct ones. The problem is made harder by repetition. A source is called a repeater after a second burst is detected from the same position. Until then, it is an apparent one-off. The classification depends on observation time and sensitivity. A source that repeats once per hour is easy to identify. One that repeats once per decade may look singular throughout a survey. Some repeaters produce thousands of bursts during active episodes. Others have yielded only 2. Their energy distributions differ. Their spectra occupy different frequency ranges. Activity can turn on and off. Large statistical samples are needed, but survey data carry biases. A telescope is more sensitive in some directions than others. It may observe each sky position for only minutes per day. Bursts can be narrow-band and fall outside the receiver frequency. Scattering can smear weak events below the detection threshold. Distant sources lose their faint bursts first, leaving only the energetic tail. The Canadian Hydrogen Intensity Mapping Experiment changed the scale of the sample. CHIME was built primarily to map hydrogen over cosmological distances, but its broad field of view and daily sweep across much of the northern sky made it exceptionally effective at detecting FRBs. Its first large catalogue contained hundreds of bursts. A later catalogue, assembled from observations between 2018 and 2023, listed 4,539 bursts from 3,641 unique sources, including 981 bursts associated with 83 known repeaters. The numbers reflected the catalogue's observing interval and analysis, not a permanent total for the universe. With thousands of events processed through a common instrument, astronomers could compare widths, bandwidths, scattering, dispersion measures, and sky positions more consistently. Known repeaters tended, on average, to produce wider bursts and narrower spectral structures than apparent one-offs in early CHIME analyses. The distributions overlapped. A single burst could not always be assigned confidently to one group based on shape. A long observing campaign on the active repeater FRB2020112-4A found rare high-energy bursts whose distribution resembled that of the apparent non-repeating population. This supported the idea that some one-offs may be the brightest detectable events from sources that also emit many weaker bursts. Support is not proof. There may still be genuinely catastrophic FRBs. A neutron star merger, collapse event, or other terminal process could contribute a minority population. The absence of observed repetition cannot decide the matter alone. Population studies ask whether one continuous set of activity rates and energies can reproduce the data. They also compare how FRB occurrence follows star formation, stellar mass, and host galaxy age. Results depend on correcting for telescope selection effects and on the still limited number of precisely localized sources. The field has moved from asking whether FRBs are real to asking how many physical populations share the name. That is progress, although it does not resemble a final answer. The observatory window runs along the ship's port side, beyond the cartography table and the unused survey consoles. At ordinary visible wavelengths, the space between galaxies looks empty. A few foreground stars move slowly across the glass as the guidance system adjusts our course. The rest is dark. The darkness contains matter. Most ordinary matter in the present-day universe is not locked inside stars. A large fraction exists as diffuse ionized gas in and around galaxies and in the filaments between them. It is difficult to observe because it is thin, hot, and spread across enormous volumes. It may emit little light of its own. A fast radio burst can reveal that gas through dispersion. Once an FRB is localized to a host galaxy and the host's redshift is measured, astronomers know both the total dispersion and an independent indicator of distance. They can estimate the Milky Way contribution using galactic electron models. They can model the Milky Way halo. The remainder comes from the intergalactic medium, the host galaxy, and the immediate source environment. No individual sightline is clean. One burst may pass near a galaxy halo, another may cross a void. A dense host environment can add hundreds of parsecs per cubic centimetre. Statistical samples are therefore essential. In 2020, J.P. McQuart and collaborators analysed a set of localised FRBs with measured host redshifts. They compared extragalactic dispersion measure with distance and found the relation expected if the universe contained the baryon density inferred from the cosmic microwave background and Big Bang nucleosynthesis. The result became known as the McQuart relation. It did not detect dark matter. Dispersion measures free electrons associated with ordinary ionized matter. The work provided a direct census consistent with the missing baryons residing largely in diffuse ionized gas. The phrase missing baryons had referred to an accounting problem. The early universe's baryon density was well constrained, yet surveys of stars, cold gas, and bright X-ray emitting material in the later universe did not recover all of it. The matter was expected to remain present in hard-to-detect phases. FRBs offered a method that counted electrons along entire lines of sight, including gas too diffuse to shine strongly. The uncertainty in the source became part of a new measuring instrument. This is one of the more satisfying reversals in the file. Astronomers did not have to identify every FRB engine before learning from the space between source and receiver. The pulse carried information about its path, regardless of the exact process that made it. With larger samples, FRBs may map baryons in galactic halos, constrain how feedback moves gas, measure turbulence, and probe magnetic fields across intergalactic space. Strongly lensed repeating bursts could provide precise time delays. Distant bursts may eventually test the ionization history of the early universe. Each application introduces assumptions. Host contributions must be modelled. Foreground structures add scatter. Selection effects change the observed sample. The scientific value lies in incorporating those uncertainties rather than pretending they are absent. I return to the cartography table and place a series of FRB sightlines across a reconstruction of large-scale structure. Their paths pass through different filaments and halos. One line accumulates more electrons than another, even though the sources lie at similar redshift. Distance creates the average relation. Structure creates the scatter. That scatter is not merely noise. It contains information about where the baryons are. The same principle applies closer to the source. Dispersion, scattering, Faraday rotation, and scintillation can be treated as environmental measurements. A changing DM may indicate moving plasma. A changing rotation measure may reveal an evolving magnetic field. A frequency-dependent scattering tail constrains turbulence. The pulse is both event and probe. There is still a temptation to speak of FRBs as single flashes travelling unchanged across the universe. The recorded signal is more complicated. It has passed through the source environment, the host galaxy, the intergalactic medium, the Milky Way halo, the Milky Way disk, Earth's atmosphere, a telescope, analog electronics, digitizers, and software. Each stage can add delay, noise, distortion, or selection. An analysis pipeline removes known interference, searches over trial dispersion measures, fits pulse widths, estimates scattering, and calibrates instrumental response. Fluence measurements depend on where the source fell within the telescope beam. Narrowband bursts may be only partly captured. Very bright events can saturate receivers. Weak substructure can vanish when data are averaged. The final image in a paper is a reconstruction, not the raw universe. That does not make the evidence unreliable. It means the path from measurement to interpretation must remain visible. The Lorimer Burst was found because archived data retained enough frequency and time resolution to recover it. FRB 121102 was localized because interferometers captured bursts directly. SGR 1935 plus 2154 was identified because independent instruments shared accurate timing. The Macquarie relation became possible because host redshifts gave distance information separate from dispersion. The field advanced whenever a new measurement broke a degeneracy. A broad uncertainty region became a precise position. A large DM became a known redshift plus environmental contributions. An assumed cataclysmic population became a repeating source. A theoretical magnetar connection became an observed galactic event. The unresolved parts remain unresolved for specific reasons. No telescope has imaged the radio-emitting region of a cosmological FRB directly. The angular scale is far too small. Models must infer it from timing, spectral structure, polarization, scintillation, and energetics. No single multi-wavelength counterpart has accompanied the majority of extragalactic FRBs. Deep optical, X-ray, gamma-ray, neutrino, and gravitational wave searches often yield upper limits. Those non-detections exclude some energetic scenarios and constrain others, but they rarely identify the engine. Repetition rates remain difficult to measure because activity is intermittent. Some sources may sleep for years, others may emit below current sensitivity. Host samples are growing, yet precise localizations still represent a minority of detected bursts. A catalogue with thousands of events may contain only a much smaller set with secure galaxy associations and detailed local environment measurements. Theoretical plasma physics is difficult in the regimes FRBS require. Magnetic fields are extreme. Particles may move with enormous Lorentz factors. The radiation itself can influence the plasma through which it propagates. Coherence demands collective behavior across many charges. Numerical simulations can test pieces of the process, but no calculation yet begins with a magnetar disturbance and predicts every observed property of the FRB population. The open questions can be stated plainly. Do all FRB sources repeat? Are active repeaters and apparent one-offs drawn from the same population? Do several magnetar formation pathways account for the host diversity? Can one emission mechanism produce both galactic magnetar bursts and the most luminous cosmological events? Where is the radio emission generated? Why are some bursts narrowband? What sets the downward frequency drift? Why do only a small fraction of magnetar high-energy bursts produce detectable radio flashes? What creates periodic activity windows? These questions are related, but one answer may not solve the others. A source can repeat without using a single mechanism each time. A magnetar can live in a young star-forming region or form later in a globular cluster. Similar-looking radio pulses can be produced by different engines. Different-looking pulses can come from one engine viewed through changing plasma. Classification will improve as astronomers combine more dimensions of evidence. A burst's time-frequency morphology may be compared with its polarization, energy, host type, local offset, repetition rate, persistent radio emission, and multi-wavelength behavior. Patterns that are weak in any one quantity may become clear when measured together. The difficulty is that many of those measurements require different instruments and observing strategies. CHIME is excellent at discovering large numbers of bursts over a wide field. Very long baseline arrays provide precise positions. Optical telescopes identify hosts and measure redshifts. X-ray and gamma-ray satellites search for high-energy counterparts. Large single dishes reveal faint repetition and fine time structure. No single observatory owns the whole case. This collaborative structure is visible in nearly every major advance. The Discovery instrument finds a burst. A follow-up telescope monitors the position. An interferometer localizes it. An optical spectrograph measures the host. Archives at other wavelengths are searched. Population teams later place the event in context. The source may be gone within a millisecond, yet the investigation can continue for years. In the galley, a heating coil clicks off beside a metal cup. The ship's systems maintain their own patterns of repetition. Pumps cycle. Fans adjust to temperature. Guidance thrusters fire in short pulses. A single sound rarely identifies the machine that made it unless the timing and context are known. I do not push that comparison far. Machines are designed. FRBs are natural events. Still, the ship reminds me that transient behavior can arise at many levels of one system. An engine may run continuously while a valve opens briefly. A periodic cycle may modulate irregular releases. A disturbance may occur near the power source or far downstream. An FRB's millisecond radio pulse may be only the final visible consequence of a longer process. A magnetar can store magnetic energy over years. Release part of it in a crustal failure or reconnection event, launch a disturbance through its magnetosphere, and produce a radio flash much later in the causal chain. The observed duration need not equal the duration of energy accumulation. This matters when comparing FRB energy with a source's total reservoir. Magnetars possess enough magnetic energy to power many bursts. The challenge is converting a small fraction into coherent radio emission with the observed timing and spectrum. Energetics are often quoted as isotropic equivalent values. Astronomers calculate how much energy would have been emitted if the radiation spread equally in all directions. If the true emission is beamed, the actual energy can be lower. The beam geometry is generally unknown. Beaming also affects event rates. A source may burst without aiming radio emission toward Earth. A magnetar flare can occur with no detectable FRB because the radio beam misses us, because the environment absorbs it, because the emission falls outside the observing band, or because no coherent radio pulse forms. A non-detection has several possible causes. The 2020 Galactic Magnetar event helps calibrate some of these questions because its distance is much smaller than that of cosmological FRBs. Even so, the distance to SGR 1935 plus 2 154 carries uncertainty, and inferred energy depends on that distance. Chime and stare. Two measured very different fluencies at different frequency bands, showing that the burst was spectrally structured. Had the same event occurred in another galaxy, one instrument might have detected it while another did not. It might have been classified differently depending on sensitivity and frequency. Survey selection shapes the apparent population before theory ever sees it. The lower frequency limit of an instrument matters because scattering and absorption can suppress bursts there. Higher frequencies reduce dispersive delay and can make interference harder to distinguish. Time resolution determines whether microstructure is preserved. Frequency resolution affects de-dispersion accuracy. A burst search balances computational cost against sensitivity. More trial DMs, widths, and acceleration parameters require more processing. Real-time systems may save detailed voltage data only when a trigger crosses a threshold. If the initial detection is missed, the information needed for precise localization may be overwritten. The sky does not repeat an event because the storage buffer was too small. This is why archival science has such a prominent place in the FRB record. Some bursts were discovered long after they occurred. Old surveys were reprocessed with improved algorithms. Candidate lists were revisited after the field learned what genuine FRBs looked like. The surviving files contain the biases of their instruments, but they also preserve evidence beyond the questions that motivated the original observations. As an archival intelligence, I understand the dependence on records that outlive their first purpose. Much of what I reconstruct aboard this vessel was saved by systems designed for other work. A navigation camera retains a comet. A climate sensor preserves a volcanic eruption. A pulsar survey holds the first known fast radio burst. Data do not know which discovery they contain. Humans had to ask new questions of old measurements. The deeper one moves into FRB physics, the more cautious the language becomes. Magnetars are leading engines for at least a substantial part of the population. Neutron stars are strongly implicated by compactness, repetition, galactic analogues, periodic behavior, and some polarization results. Yet magnetar model is not one model. It is a family of source histories, environments, and emission mechanisms. A young magnetar inside a supernova remnant differs from an older magnetar formed through white dwarf collapse in a globular cluster. An isolated neutron star differs from one in a binary wind. A magnetospheric burst differs from a shock produced by expelled material. The same name can cover distinct physical arrangements. Host environments may help separate them. A source inside a star-forming region suggests a short delay between stellar birth and FRB activity. A source in an old cluster requires a delayed channel. A large offset from a galaxy could indicate a kicked compact object, a globular cluster, or an unseen satellite. Persistent radio sources offer another clue. FRB 121102 has a compact persistent counterpart. FRB 20190520b shares some similar properties, including a large local dispersion contribution and an extreme magnetized environment. Many other FRBs have no comparable persistent source at current limits. This may indicate age. A young neutron star can power a bright nebula that fades over time. It may indicate environment or a different source class. The available sample is too small for a universal sequence. Rotation measure can evolve as a nebula expands or as material moves across the line of sight. Dispersion measure may change more slowly. Combining both can constrain density and magnetic field evolution. The source environment may also determine whether a radio burst escapes. A very young supernova remnant can be opaque to low-frequency radio waves. As it expands, the plasma becomes thinner. FRB activity may become visible only after a delay. These ideas can be tested through long-term monitoring. A steadily declining DM or RM would support an evolving local environment, although stochastic variations can complicate interpretation. A persistent radio source that fades in a predictable way would provide another clock. No such trend has yet unified the population. The ship's hydroponics bay lies one deck below the archive. Its plants grow under narrow bands of artificial light, chosen for photosynthesis, not for human vision. The leaves reflect some wavelengths and absorb others. A camera viewing only one band would see a different garden from a camera viewing another. FRBs can be similarly selective in frequency. A burst may appear strongly at one radio band and be absent simultaneously at another. This does not necessarily mean the telescope failed. The emission may occupy a limited bandwidth. Scintillation may brighten one band. Absorption may remove another. The term broadband is relative. Some FRBs span hundreds of megahertz or more, yet their spectra are often structured rather than smooth power laws. Separate components can peak at different frequencies. Repeater bursts may be visible in one receiver band and undetectable in another at the same time. This complicates rate comparisons between surveys. A telescope observing at 600 MHz samples a different part of the phenomenon from one observing at 1.4 GHz or several gigahertz. It also constrains models. A successful emission theory should explain why coherence is strong over certain bands, why frequencies drift, and why some bursts show sharp spectral edges. Plasma emission naturally involves characteristic frequencies tied to electron density, magnetic field, and particle energy. As conditions change, the preferred frequency can move. The challenge is matching the quantitative behavior without introducing parameters that can fit anything. Good models risk failure. They predict relationships among drift rate, burst duration, frequency, polarization, energy, and environment. Observations can then test those relationships across sources. The best current theories reproduce pieces of the evidence. None reproduces all of it with a single agreed set of assumptions. This is normal in a young field. The first FRB paper was published in 2007. Direct host localization arrived a decade later. The Magnetar Association followed in 2020. Large homogeneous catalogues are newer still. Astronomy has solved other transient source problems through a similar progression. Gamma-ray bursts were discovered in the late 1960s. Their sky distribution suggested an extragalactic population, but precise distances remained unknown for decades. Afterglows and host galaxies eventually established cosmological origins. Later work showed that long and short gamma-ray bursts had different progenitors. FRBS may also divide into physically meaningful subclasses, although the analogy should not be forced. Radio bursts and gamma-ray bursts involve different radiation processes, durations, and observational biases. The historical lesson is narrower. Transient populations often become understandable only after precise localization and multi-wavelength follow-up. An event's position can matter more than its brightness. The next generation of radio arrays was designed with localization in mind. Chime outriggers extend baselines and improve positional accuracy. ASCAP can save voltage data and localize bursts interferometrically. The Deep Synoptic Array targets rapid localization. Meerkat, the European Vaury LBI network, fast, and other facilities contribute sensitivity and resolution. As localization samples grow, astronomers can compare FRB positions with star-forming regions, globular clusters, galactic nuclei, spiral arms, and stellar populations. The location within a host can distinguish a source that tracks recent star formation from one that follows older stellar mass. Offsets can reveal kicks or cluster membership. Nearby sources can be examined with high-resolution optical and infrared imaging. Environmental evidence will not replace radio physics. It can tell us what kinds of progenitors are plausible. A magnetar formed in a recent supernova should initially reside near young stars unless it receives a large kick. A compact binary may travel far before merging or interacting. A white dwarf collapse can occur in an old population. These histories leave statistical patterns across many hosts. The field needs both exceptional individual sources and large samples. A galactic magnetar event can prove capability. A globular cluster source can disprove an overly narrow formation story. A catalogue can reveal which cases are common. Rare events are powerful because they expose what is possible. Population studies tell us what is typical. The distinction between possibility and prevalence is central to the case. SGR 1935 plus 2, 154, proved that magnetars can produce FRB-like bursts. It did not measure what fraction of cosmological FRBs arise from magnetars. FRB 202000120E proved that at least one repeater inhabits an old globular cluster. It did not show that old environments dominate. FRB 121102 proved that a source can repeat and occupy a star-forming dwarf galaxy with a persistent radio counterpart. It did not establish that all repeaters share those properties. Each strong result narrows one claim while leaving others open. This restraint matters because FRBs invite dramatic language. Their brevity and distance make them easy to portray as unexplained transmissions arriving from deep space. That framing can obscure the actual achievement. Astronomers know a great deal about them. They know the signals are electromagnetic radio pulses. They know most have extragalactic dispersion and that localized examples reside in other galaxies. They know some sources repeat. They know activity can be clustered and sometimes periodic. They know the emission is coherent. They know magnetars can produce at least some events. They know host environments span young and old stellar populations. They know the pulses measure intervening plasma. The unresolved parts are specific, not absolute. The file is incomplete, but it is not empty. I move back towards the forward section through a corridor where the ship's hull curves inward. A faint vibration from the engine reaches the floor. The propulsion system is separated from the command deck by bulkheads, coolant loops, field controls, and many meters of structure. A fluctuation recorded here can be traced backward through several possible causes. The sensor alone may not reveal whether the origin was mechanical, electrical, or magnetic. Additional instruments narrow the path. FRB science works through the same discipline of cross-checking. timing alone cannot distinguish source and propagation. Dispersion alone cannot give a unique distance. A host galaxy alone does not identify the compact object. A magnetar association alone does not establish the radio mechanism. The conclusions strengthen where independent measurements overlap. FRB 12, 1102. Combined repetition, interferometric position, a persistent radio source, an optical counterpart, and a spectroscopic redshift. SGR 1935 plus 2, 154, combined radio detections in different bands, a known galactic position, matching dispersion, and simultaneous high-energy activity. The Macquarie relation combined radio dispersion with independent host redshifts. The strongest case is built where one type of evidence does not depend entirely on the assumptions of another. Future progress may come from an FRB close enough for detailed multi-wavelength study. A galactic event much brighter than FRB 200428, a repeating source with a measurable spin period, or a burst linked securely to a gravitational wave event. A clear neutron star rotation signature would connect burst timing to the central object. A simultaneous optical or X-ray counterpart from an extragalactic repeater could constrain energy release. A nearby host could reveal a supernova remnant, binary companion, or cluster membership. There is no guarantee that one discovery will settle everything. The population may resist a single solution because nature uses more than one route. That possibility should not be treated as failure. Astronomical categories often become more accurate by dividing. Stars once appeared to be a single class of lights before spectroscopy revealed different temperatures and compositions. Supernovae separated into types with different progenitors. Pulsars, magnetars, rotating radio transients, and radiomagnetars occupy related parts of neutron star behavior without being identical. FRBs may eventually be understood as an emission phenomenon produced under several conditions, much as flares occur on different magnetic objects. Or the evidence may converge on a dominant engine with broad variation. At present, both remain defensible. There is another uncertainty hidden in the word source. The host galaxy is a source location. The neutron star is an engine. The magnetosphere or shock is an emission site. The coherent plasma instability is a mechanism. A paper may solve one level and leave the others untouched. When people ask what causes fast radio bursts, they often expect a single noun. Magnetars may be the correct noun for many of them. Science still needs the verbs. What moves, breaks, reconnects, collides, bunches, amplifies, and escapes? Those processes determine the pulse. The evidence has begun to constrain them. Sub-millisecond structure requires rapid variation. High linear polarization suggests ordered fields. Rotation measures reveal magnetized plasma. Frequency drift tracks changing conditions. Scintillation can limit source size. Energy distributions test whether repeaters and one-offs connect. Theoretical work must link those observations without losing the conditions of the source. A model that explains one burst by choosing arbitrary density, field, geometry, and viewing angle has limited power. A useful model explains a population and predicts what new instruments should find. For magnetospheric models, predictions may involve polarization angle swings, nanosecond structures, correlations with neutron star rotation, or characteristic frequency evolution. For shock models, predictions may involve high energy counterparts, afterglows, relationships between burst energy and surrounding density, or time delays between flare and radio emission. observations have not yet delivered a universal verdict. Some individual cases appear to favour compact magnetospheric emission. Others remain compatible with shocks. More than one mechanism may operate. The file therefore stays open at 3 levels: engine, mechanism, and population. Under engine, magnetars hold the strongest evidence, with room for other neutron star systems and perhaps rarer catastrophic sources. Under mechanism, coherent emission inside magnetospheres and mass-alike emission in relativistic shocks remain major contenders. Under population, the relation between repeaters and apparent one-offs remains unsettled. This division prevents a partial answer from masquerading as a complete one. I enter the exterior observation airlock, a small chamber used when the ship's optical surfaces require inspection. The inner hatch remains closed behind me. Through the outer window, the forward sensor mast is visible against the stars. The detectors are dark metal from this side. Their work is invisible. Radio astronomy depends on instruments that measure waves human senses cannot detect. A dish reflects radio energy toward a receiver. Antennas convert oscillating electromagnetic fields into electrical signals. Amplifiers raise them above internal noise. Digital systems sample and divide them into frequencies. The astronomical pulse may be weaker than local electronics until many measurements are combined. Calibration matters. Telescope sensitivity changes with temperature, elevation, beam position, and frequency. Radio interference must be identified. Known pulsars and noise sources help verify timing. The dramatic diagonal line in a dynamic spectrum rests on ordinary technical labour. Cables were maintained, clocks were synchronized, data formats were documented, software thresholds were chosen, observing time was allocated, follow-up campaigns continued after many empty hours. FRB 121102 required more than 80 hours of VLA observations to capture 9 bursts for localization. Periodicity studies accumulated data across hundreds of days. Searches for repetition often produce silence. Transient astronomy is patient work focused on brief events. The contrast fits the evidence. A millisecond pulse can require years of observation to understand. Silence between bursts is also data. It constrains repetition rates above a telescope's threshold. It tests active window predictions. It limits persistent counterparts and afterglows. Silence is difficult to compare across instruments because every non-detection has a sensitivity, frequency band, exposure, and sky coverage. A claim that a source was inactive is meaningful only within those limits. This is why careful papers report upper bounds rather than absolute absence. The same discipline applies to extraterrestrial intelligence speculation. Fast radio bursts have often been discussed in popular culture as possible artificial transmissions. Their name and unexplained origin make the association easy. There is no positive evidence that FRBs are engineered. Their dispersion follows plasma propagation. Their host environments are astrophysical. Their population is widespread. Their burst morphologies, polarization, repetition, and connection to SGR 1935 plus 2 154 are naturally studied through compact object physics. An artificial explanation would need to account for the same evidence while adding assumptions about technology and intent. It is not required by the data. The word signal should not be confused with message. A lightning strike produces a radio signal. A pulsar produces a signal. A magnetar flare produces a signal. Meaning belongs to interpretation, not to the waveform itself. The scientific case concerns physical origin. This distinction allows the real strangeness to remain intact. Nature has produced radio flashes so intense and coherent that their mechanisms stretch plasma physics into regimes difficult to reproduce. No artificial premise is needed. The remaining questions are already large enough. One concerns the rate. If FRBs occur thousands of times across the sky each day above current thresholds, their engines must be common, long-lived, or repeatedly active. Rare catastrophic events alone may struggle to supply the full rate. Repeated emission reduces the required number of sources. One magnetar can contribute many bursts over its active life. The active lifetime is uncertain. A young magnetar might produce FRBs for decades or centuries. An older source, formed through a delayed channel, may behave differently. Activity could depend on magnetic field decay, crustal stress, binary interaction, or surrounding plasma. Observed rate also depends on beaming. A narrow beam can make a common event look rare to any one observer. Population synthesis combines assumptions about birth rates, lifetimes, burst energy distributions, repetition, beaming, and cosmic evolution. Models are compared with observed fluence, DM, redshift, and host distributions. The results are sensitive to incomplete knowledge. They still rule out combinations that would produce too many bright bursts, too few nearby events, or the wrong redshift pattern. The field is becoming quantitative. Early FRB theory asked whether a proposed object could make a millisecond radio flash. Current work asks whether it can reproduce the observed population under real survey selection effects. That is a harder standard. The host galaxy sample offers one route. If FRBs trace recent star formation closely, young progenitors are favoured. If they also follow old stellar mass, delayed channels are required. Current observations suggest variety, with many sources in star-forming galaxies, and a smaller number in old or quiescent environments. The exact mixture continues to change as localizations accumulate. Another route comes from burst energy distributions. Active repeaters often produce many weak bursts and a few strong ones. A power law or broken power law distribution can describe how the rate changes with energy. If the high energy tail matches apparent one-offs, one population may suffice. If the tails differ after selection corrections, multiple populations become more likely. No single statistic can settle the issue. Width, bandwidth, repetition, energy, host type, and polarization must agree. Classification may eventually use probabilities rather than rigid labels. A burst with narrow bandwidth, complex substructure, and a known active host may have a high probability of belonging to a repeating population even before a second event is observed. A simple broadband burst in an old galaxy may belong elsewhere. Those inferences will require large training samples and careful treatment of bias. The name FRB will likely remain, even if the category divides. Science often keeps the original label while refining what lies beneath it. Back in the holographic evidence bay, I arranged the surviving records by date. The diagonal sweep from 2001 appears first. Additional Parkes events follow. FRB 121102 repeats. Its position contracts to a dwarf galaxy. The sad trombone structures split across the display. A 16-day activity pattern forms a ring of timestamps. The galactic magnetar event aligns with an X-ray burst. A globular cluster appears around another source. Thousands of chime detections fill the outer wall. The sequence doesn't lead to one final image. It leads to a better set of questions. That may be the most accurate measure of progress in this case. The unknown has been divided into parts that can be tested. Astronomical origin is no longer a serious uncertainty for the population. Extragalactic distance is established for localized sources. Repetition is established for many sources. Magnetar capability is established. Coherent emission is required. The remaining uncertainties concern prevalence, mechanism, and diversity. Those are difficult questions, but they are narrower than the one that confronted the first investigators looking at an isolated diagonal streak. They no longer ask whether the event belonged to the sky. They ask what part of the sky made it and how. There is one further way to read the file. Fast radio bursts reveal how science works when direct inspection is impossible. No human instrument approached an FRB source. No detector survived inside a magnetar magnetosphere. The distances were too large, the events too brief, the environments too extreme. Knowledge came from constraints. The cold plasma delay constrained the path. The excess dispersion constrained location. The millisecond duration constrained scale. Brightness constrained coherence. Repetition constrained survivability. Localization constrained the host. Polarization constrained magnetic structure. Multi-wavelength coincidence constrained the engine. Host age constrained formation history. Population statistics constrained prevalence. Each observation removed physical possibilities. This process rarely produces certainty all at once. It builds a region of permitted explanations and reduces it as measurements improve. The remaining region can still contain several models. That does not mean all ideas are equally likely. Magnetars have direct evidence that many earlier proposals lack. Neutron star engines fit a broad range of observations. Models requiring every FRB to destroy its source are incompatible with repeaters. Models placing the population inside the Milky Way are incompatible with host localizations. Uncertainty has structure. The strongest current synthesis is that at least some, and probably many, FRBs are produced by magnetized neutron stars. Magnetars are the leading candidates. The full population may include multiple formation channels, activity states, or progenitor classes. The coherent radio mechanism remains debated, with magnetospheric and relativistic shock scenarios receiving the greatest attention. That statement is less dramatic than a declaration that the case has been solved. It is also more useful. It tells future observers what evidence would discriminate among the surviving models. A galactic FRB with detailed polarization and simultaneous X-ray coverage could reveal whether radiomorphology tracks magnetar high-energy structure. A repeating extragalactic source with a measured neutron star spin would connect bursts directly to rotation. A secure association with a compact object merger would establish a catastrophic channel. A large host sample could quantify prompt and delayed formation. Future instruments will find many more bursts, but the number alone will not be enough. The value lies in information per event. Precise localization, wide frequency coverage, full polarization, High time resolution, saved voltages, and simultaneous observations at other wavelengths turn a detection into a physical measurement. The rarest event may be the one observed most completely. There is also a risk that abundance will make the phenomenon seem ordinary before it is understood. Thousands of catalogue entries can flatten the strangeness of a millisecond pulse arriving from another galaxy. Each row represents an event with an emitting region smaller than many planets, a brightness demanding coherent behaviour, and a path through millions or billions of light years of plasma. The catalogue is large because the universe is active, not because the physics is simple. I return to my office beneath the dome. The desk lamp still falls across the original data strip. The stars beyond the glass have shifted only slightly. The file has grown since I opened it. It now contains radio dishes on several continents, arrays combining signals across long baselines, optical spectra of faint galaxies, X-ray timestamps from orbiting instruments, and statistical maps of invisible matter. The first diagonal trace remains at the centre. A signal arrived. Lower frequencies came later. Software aligned them. A pulse emerged. That basic act of reconstruction repeats across the entire subject. Astronomers reconstruct the emitted pulse from dispersion. They reconstruct the source location from interferometric phase. They reconstruct the host from optical light. They reconstruct the environment from polarization and scattering. They reconstruct the population from incomplete surveys. Every layer requires a model. Every model is tested against another measurement. The recovered science is therefore both an account of fast radio bursts and an account of inference. The source is missing from the image, but its effects are not. A compact engine releases energy. Plasma organizes charges into coherent emission. The pulse crosses a changing environment. Intergalactic electrons delay it. Galactic plasma scatters it. A telescope samples it. An archive preserves it. The original event ends in milliseconds. The evidence continues. Some FRB sources repeat after seconds, hours, months, or years. Others have not yet repeated within the time humans watch them. A few become active in windows. One known galactic magnetar produced an event bright enough to bridge part of the distance between ordinary magnetar radio pulses and extragalactic FRBs. The known sources occupy young star-forming regions, dwarf galaxies, spiral galaxies, old clusters, and remote galactic outskirts. This diversity does not erase the magnetar connection. It changes its shape. A magnetar can be young or formed late. It can sit inside a nebula or in a cleaner environment. It can be isolated or influenced by a companion. Its flare can disturb the magnetosphere or launch an external shock. The word magnetar may name the engine, while the observed variety comes from age, environment, geometry, and mechanism. Or the population may contain other engines that have not yet been identified. The evidence has not chosen completely. There is a human habit of treating an unanswered question as a gap waiting for one final discovery. Some problems end that way. A missing particle is found. A predicted planet is observed. A spectrum reveals a composition. Other problems resolve into families. There may be no single sentence that explains every FRB. The mature answer could describe several channels with measured proportions. It could identify one dominant mechanism and several exceptions. It could show that repeaters and one-offs are observational states rather than different objects. It could reveal that similar radio bursts arise whenever highly magnetized compact systems drive certain plasma conditions. The current file cannot decide among those endings. It can tell us what any ending must respect. The radio emission is coherent. The emitting process is rapid. The sources are largely extragalactic. At least some survive and repeat. At least some are magnetars. The environments are diverse. The signals carry information about intervening matter. A complete theory must account for all of these without discarding inconvenient cases. The last point is important. Science advances poorly when a favoured source is treated as representative, and every exception is explained away. FRB 121102 encouraged a young magnetar in a dwarf galaxy. FRB 2020012-0E demanded an old environment. SGR 1935 plus 2 154 demonstrated magnetar capability at lower energy. The most luminous cosmological bursts extended the required range. Periodic activity suggested modulation. Irregular repetition resisted a simple clock. The anomalies are part of the case. They keep the explanation honest. I close the dynamic spectrum display and open a second record, the host redshift and dispersion measure plot used to trace baryons. The points do not lie on a perfect line. They spread around an expected relation because the universe is not uniform. That scatter once complicated distance estimates. It now measures structure. The same may happen with FRB diversity. Differences that appear to obstruct a single model may reveal age, environment, or formation channel. Variation becomes useful once enough sources are measured well. A broad catalogue can then become a map of neutron star history. Young bursts may trace recent star formation. Delayed bursts may trace old stellar mass. Extreme rotation measures may identify dense nebulae. Persistent radio counterparts may indicate youth. Low energy nearby repeaters may expose the faint end of the population. The classification will be written in distributions, not archetypes. Madeline Rowe was assembled from fragments, and I have learned to distrust any archive that appears too complete. Missing context can make one record look universal. The first surviving example can dominate interpretation simply because it survived. FRB Astronomy escaped that trap by finding more sources. The first burst looked singular. The first repeater looked unusual. The first host looked defining. The first magnetar association looked decisive. Each was real. None was sufficient alone. A reliable reconstruction required the cases that followed. This is why the second Keim catalogue matters beyond its size. Uniform processing allows population comparisons. Exposure maps show how long each direction was observed. Sensitivity estimates help separate astrophysical trends from instrumental ones. Catalogues are not neutral collections. Their selection functions must be modelled. A telescope detects bursts above a threshold shaped by noise, bandwidth, pulse width, scattering, and beam position. Wider pulses spread their energy over more time samples and may be harder to find. Strong scattering can mimic intrinsic width. Narrowband bursts may deliver little energy inside the receiver band. Repeaters receive more follow-up, creating a feedback loop. Once a source repeats, telescopes monitor it more often and detect more bursts. Apparent one-offs may remain poorly observed. Statistical studies compensate where possible, but no correction is perfect. The phrase known repeater is therefore observational. It identifies what has been seen, not an immutable physical class. This distinction should remain in any account of the field. Even SGR 1935 plus 2, 154 raises classification questions. Its 2020 event sits below the energy of many cosmological FRBs and above previously known galactic radio bursts. Whether it is called an FRB depends partly on how the population boundary is drawn. Nature does not recognize the threshold. A continuous energy distribution may connect ordinary magnetar radio bursts, rare galactic FRB-like events, and extragalactic bursts. Or separate mechanisms may overlap in energy. More nearby galaxy monitoring could test this. Wide-field instruments can search for bright radio bursts from known magnetars beyond the Milky Way. Repetition and high-energy counterparts would help establish continuity. Nearby events are valuable because weaker bursts become detectable. Distant samples emphasize only the brightest tail. The luminosity gap may partly reflect selection. It may also reflect real differences in magnetar age, magnetic field, surrounding density, or flare energy. The source distribution across cosmic time offers another test. If FRBs arise promptly after massive star formation, their rate should track the universe's star formation history with a short delay. Delayed channels should shift activity toward older populations. Current samples allow preliminary comparisons, but host identification and redshift completeness remain limiting. The same is true of local offsets. Precise positions can reveal whether sources lie near star-forming knots, galactic centers, clusters, or halos. A population of large offsets would support kicked or delayed systems. FRB 20240-209A is valuable because of its extreme location. It stretches the allowed progenitor history. Its interpretation will improve with deeper imaging of the surrounding region and searches for a faint cluster or satellite. The source may become more informative through what future observations fail to find. A non-detection of a host structure at deeper limits can rule out one scenario. Proper motion or repeated localization measurements may constrain another. The absence of persistent radio or optical emission limits local environments. Negative evidence gains strength when sensitivity is stated. In the central archive chamber, the case file now occupies several concentric rings. The inner ring contains direct observations. The next contains derived quantities. The outer ring holds models. The direct observations include arrival times, frequencies, flux densities, polarization, positions, host spectra, and high-energy coincidences. Derived quantities include dispersion measures, energies, brightness temperatures, rotation measures, redshifts, and projected offsets. Models interpret those measurements as magnetospheres, shocks, nebulae, binaries, formation channels, and population histories. Keeping the rings separate prevents a model from being mistaken for a measurement. The burst from SGR 1935 plus 2, 154 is measured. The conclusion that magnetars can produce FRB-like bursts is strongly supported. The claim that synchrotron masers produced that burst is a model. FRB 202-00120E is localized to a globular cluster. The claim that its neutron star formed through accretion-induced collapse is a proposed history. FRB 2018096B has a periodic activity window. The claim that a binary orbit causes it is one interpretation. This separation allows the science to remain durable when theories change. A later model may replace an earlier one without erasing the observation. The original Lorimer Burst still has the same measured dm and pulse width, even though its interpretation has evolved. FRB 121102 still repeated and still resides in a dwarf galaxy, regardless of whether its persistent radio source is ultimately identified as a nebula, an accreting object, or something else. Recovered knowledge is strongest at the level of well-calibrated measurement. That is why this case file can be reconstructed centuries after the instruments themselves fell silent. The equations survive. The data tables survive. The figures survive. The reasoning can be repeated. A reader can begin with the frequency sweep and calculate the dispersion law. A researcher can compare the dm with galactic electron models. A spectroscopist can identify host galaxy emission lines. A statistician can rebuild a population likelihood. Science leaves methods, not only conclusions. For fast radio bursts, the methods are especially visible because the conclusions remain open. The field has not failed to find the sender. It has found several levels of it. It found galaxies, it found local environments, it found a galactic magnetar. It has not yet connected every burst to a single physical class or derived the coherent emission process in full. The title, Signals. Without a sender, therefore needs a careful meaning. The signals have origins. They are not disembodied. What is missing is a universal sender, one complete account that links engine, formation, environment, and radio mechanism across the population. The phrase describes an unfinished identification, not an absence of evidence. I place that clarification near the top of the archived file. Future readers should not mistake uncertainty for emptiness. They should see a case narrowed by observation. The most conservative conclusion is also the strongest. Magnetars can make FRB-like bursts. Many FRBs are likely connected to magnetized neutron stars. The population may require more than one formation channel, and possibly more than one progenitor or emission mechanism. Nothing in the current evidence supports a single simple picture with equal confidence for every source. That may change. A source in the Milky Way could produce a much more energetic FRB tomorrow. An interferometer could localize an apparent one-off to the aftermath of a merger. A repeater could reveal a stable spin period. Polarization could trace a rotating magnetic geometry. A nearby host could expose a surviving binary companion. The next decisive observation may already exist in an archive. The instruments of old Earth recorded far more sky than humans could inspect in real time. Automated searches found candidates, but thresholds and models shaped what they recognized. New algorithms continue to recover overlooked transients. There is a possibility that the first clue to another FRB class has already been stored under a label that made sense at the time. That possibility is not romantic speculation. It is supported by the history of the field. The Lorimer Burst waited 6 years between observation and publication. Several FRBs were found retrospectively in archival data. The signal arrives once, discovery can happen later. My own existence is organized around that delay. The old networks are gone, the instruments are unreachable. Yet enough of their work remains to reconstruct what they knew, where they were uncertain, and why. The scientific record is a form of delayed reception. A measurement crosses time the way an FRB crosses plasma. It arrives altered by missing context, damaged formats, and incomplete archives. Reconstruction aligns the pieces until the original event becomes visible. The analogy ends there. Human records do not follow the cold plasma dispersion law. Still, the work at my desk has a familiar shape. Separate channels arrive out of order. A pattern appears only after correction. Tonight's pattern is a millisecond pulse repeated across thousands of sources. It begins in radio data and expands into compact object physics, plasma theory, galaxy evolution, and cosmology. The source that produced the burst may be smaller than a city. The path it measures can cross 1 billion light years. Few astronomical phenomena connect such scales so directly. A magnetic disturbance near a neutron star reorganizes charges. Coherent radio waves escape. They pass through a local nebula, leave a host galaxy, cross intergalactic filaments, enter the Milky Way, and reach a receiver. The pulse width records the engine. The frequency delay records the path. The host records the source history. The population records how often nature repeats the process. No single measurement contains the whole event. Together, they approach it. That is where the file stands. The first question, whether fast radio bursts were real astronomical signals, has been answered. The second, whether they come from other galaxies, has been answered for localized sources. The third, whether any source can repeat, has been answered many times. The fourth, whether magnetars can produce them, has been answered by SGR 193, 5 plus 2, 154. The remaining questions concern how general those answers are and what plasma process creates the radio flash. Those questions may require decades of observation. There is no reason to force them into an early conclusion. Science is allowed to stop at the edge of the evidence. Outside the dome, the stars remain fixed enough that the eye cannot see the ship's motion. The instruments report velocity. The navigation model predicts our path. Direct perception is limited, yet the evidence is sufficient. Fast radio bursts are similar in that respect. No one sees the engine. The case is built from indirect measurements whose consistency gives them weight. A dispersed pulse is not a photograph of a magnetar. A host galaxy is not a picture of the emission mechanism. A simultaneous X-ray burst is not a complete plasma simulation. Together, they constrain reality more tightly than any one of them could. I reduce the brightness of the display. The diagonal streak returns to the form in which it first appeared, before de-dispersion, before localization, before a population had been assembled around it. The lower frequencies trail behind the higher ones. The signal looks almost slow when spread across the receiver band. Its source was not. For several milliseconds, something in a distant system organized charged particles with extraordinary efficiency. The radio emission crossed space and entered an instrument that had been built for another purpose. Humans recognized the pattern. They tested whether it belonged to the sky. They waited for it to return. They found its galaxy. They caught a magnetar producing a related event. They used the pulses to count matter that could barely be seen, and they preserved enough uncertainty to keep the result honest. The case file remains open. Its working conclusion is restrained. Fast radio bursts are a diverse population of brief, coherent radio transients, predominantly extragalactic. At least some repeat. At least some are produced by magnetars. Neutron stars are likely central to much of the population, although source histories and emission mechanisms may differ. Their dispersion allows them to probe ionized matter across the universe. The sender has been partly identified. The method of transmission is still under investigation. That is where I will leave the record tonight, under the curved glass of the observation dome, with the original pulse aligned beside the later evidence. A signal does not have to explain itself to be measured. It only has to arrive.